Alright, hey guys, and welcome back to another AP Physics C video. This is going to be another one of those major derivations that you might be tested on the AP Physics C exam. But this is going to be the magnitude of the magnetic field outside of a current carrying wire at a radial distance little r from the center of that wire. You see that there. And this current carrying wire is going to have current I, current magnitude, denoted by I. And the cable radius will just be r. That looks like this. That's not really important to the problem, but that's there for future problems. So without further ado, we'll just get right into the problem here. So whenever we're trying to measure the magnetic field, we're going to use one of two laws, the Biot-Savart law or Ampere's law. So in this situation, we're going to use Ampere's law because if we try to apply the Biot-Savart for this situation, it gets really messy really quick, right? So here, I'm going to drag this circle that I have at the bottom to the top. And the reason why I did that, I'll reveal to you in a second. Before we even talk about that, we're going to write Ampere's law down to start our derivation. So here's Ampere's law. The line integral of B dot dl is going to equal mu naught times I enclosed. Simple enough, right? So now I'm going to reveal to you why we drag that circle up there. Whenever we're working with Ampere's law, we need to have an Amperian loop enclose a current, right? So in this situation, the current that's being enclosed is going to be this current, right? This current that's going through this wire, and that, right? That's why I have this current magnitude I here. So really, I can just delete that enclosed part and just say, okay, I is the current that's being enclosed. So as I was saying, we need to have an Amperian loop enclose a current, and that's a lot like Gauss's law, which we did way earlier, I think 2 units ago. But if you remember, in Gauss's law, we enclosed a charge with a Gaussian surface, right? That was in 3D. In this situation, or in these instances, we're basically doing it in 2D. We're enclosing a current with a loop, right? So now this is called this shape, this circle that we just dragged up here, is called an Amperian loop, right? You can see kind of the symmetries along these two. We have Gaussian surfaces and Amperian loops. It's pretty cool if you think about it. I like the naming system personally. But enough about that. The Amperian loop is going to serve to tell us along the path in which we're going to integrate. And you might be thinking, path? Integrate? Whenever you have an integral, right, normally when you have conventional integrals, you'll integrate something like this, 2, 5 x squared dx, right? That's a normal integral. You've seen that in your calculus class. And this one, I happen to know, evaluates to 39, right? That's pretty normal of an integral, pretty standard. But in calculus 3, you'll encounter these things called line integrals, for Gauss's law with surface integrals, where we'll integrate along a line or a surface, right? And we don't really have integration bounds that are denoted by numbers, but rather paths and surfaces, like I said. So in this situation, this circle denotes our integration path, right? That's why we have the Amperian loop. That's why it exists. That's why we drew it. That's why we pulled it from the bottom here to the top. So enough about that. What I'm going to talk about now is why we picked a circle. I don't want to give you the wrong idea of Amperian loops, but Amperian loops can exist in many shapes. Oftentimes in AP Physics C, you will only have a circle or a rectangle. Those are the only two shapes that you'll normally be tested on. The rectangle we'll get into in another video, but today we're only going to be touching on the circle. Now you can even have an Amperian loop exist in the shape of a star, right? It's kind of a funny looking star, or a triangle. But these are really not good shapes to work with because they don't offer you a special type of symmetry that allows us to bypass the calculus 3. So there's really no point in picking those shapes as Amperian loops. The only reason why we're picking this Amperian loop in a circle, and now I'm going to get into this, the reason why we're picking our Amperian loop in this instance to be a circle is because the magnetic field produced by current carrying wires is circular, right? That's a property of electromagnetism. You should know that. Hopefully your AP Physics C teachers told you, but if you haven't heard it, you heard it now, right? So in this situation, I'm going to denote the magnetic field with this red color here. The magnetic field will travel in a counterclockwise pattern, right, as per the right-hand rule, like this in a circle. So that's pretty much what the magnetic field looks like. but you'll notice something, that it travels always along the path of the Amperian loop, along the path in which we're integrating, right? Choosing our Amperian loop to be a circle, to be a shape that follows, I guess you could say, the shape of the magnetic field, right? The behavior of the magnetic field, we get a special kind of symmetry that allows us to bypass the actual calculus 3 that Ampere's law would otherwise require, right? We did this with Gauss's law as well. If you remember, we picked, right, the certain shapes, right, like a sphere or what was the other shape? Or a cylinder for certain situations to unlock this same special symmetry, right? And I'm about to show you how that special symmetry plays in. This other vector that I want to highlight is called the dl vector, right? Along this Amperian loop, there's little dl's. And now I'm not drawing the full vector, which would otherwise look like this. I'm just drawing them kind of like this. So you can see that they're infinitesimally small pieces of the whole length, the whole length L along which this Amperian loop travels, right? So these little dl's also exist along this loop. But I want us to notice one specific thing, right? The Amperian loop, right? The dl's that belong to the Amperian loop overlap with the magnetic field for every point along this circle, right? Along this Amperian loop. You'll notice here, I'll draw them out. For every one of these dl's, the magnetic field will overlap, right? That's the symmetry we want. We want it. So now, when I compute this dot product, right? Remember that the dot product is the magnitude of the two vectors times the theta between the two. When I compute that dot product and I wonder what's the cosine of the theta between the two vectors, well, if the two vectors overlap, right, the magnetic field vector and the dl vector, for every single point along this loop, the cosine would be 0, right? So now I'll replace cosine theta with cosine 0, and if it's cosine 0 for every single point along that loop, well, I can just simplify this to 1, and 1 times anything will be itself. So I can just pull that out, and now this is my new equation, my new derived equation. Simple enough, right? So now I'm going to think about this left-hand side again, right? Let's think. The magnetic field, is it a constant or not? Because otherwise this looks like a complicated integral. Well, in this situation, actually, the magnetic field would be constant for every point along this Amperian loop. And the reason for that is because along this Amperian loop, the magnetic field only depends on the radius, right? That's kind of a characteristic of the magnetic field. So the radius at every point, because it's a circle, is going to be the same little r. Therefore, right, the magnetic field is constant, and I can pull it out of my integral. So I'll do that, and I'll get b times dl, or times the line integral of dl, is going to equal mu naught I. Bam. And now I'm going to work with the left-hand side of this integral, right? You'll see. So what you should be thinking, if you've seen that Gauss's law video, is that the line integral of dl is going to evaluate to L, plain and simple. Nothing too complicated. If you want the explanation, I'll give it to you right now. If I sum up, right, along this path, all of these little dl's, that will give me the length of that path, right? Just to rephrase what I said, if I sum up infinitely small changes in length along a certain path, that gives me the length of the path in which I'm summing on, right? Hopefully that makes sense. But now we're going to think, what exactly is that length that we just found and that we're talking about? Well, you should be thinking that the length of a circle, the length of a circular path, is equal to its circumference. So I'll write that up here. C equals L, where C is circumference, is equal to, well, what is circumference equal to? 2 pi times, well, what's the radius of our Amperian loop? It's going to be little r, right? Because that's the radius at which we want to measure the magnetic field. Therefore, that's the radius in which our Amperian loop has to take on, right? So now I'll sub that in for L, 2 pi r is equal to mu naught I. Now I'll just divide out 2 pi r in order to get my magnetic field isolated, and I get that the magnetic field is equal to mu naught I divided by 2 pi r for a current carrying wire. If you want the direction, you can use your right hand rule. And if you'd like a video on the right hand rule, please let me know. I'd be happy to make one. But hopefully this video helped you guys understand a little bit more about this application of Ampere's law. But this is one equation you should definitely know by heart and be able to recall cold on the exam. It will show up on the multiple choice and on the free response. It did for my exam this year on question 4, and it did on my multiple choice as well. So definitely memorize this equation. But before I finish this video, we're just going to recap what we did. So first, we applied Ampere's law by writing it out. Then we worked with the right-hand side of the equation, taking out the enclosed by identifying the enclosed current and replacing it with its respective variable. Then we worked with the left-hand side equation by taking out this dot product by just computing it and picking an Amperian loop that allowed us for some special symmetry that allowed for the dot product to be computed easily, right? And then we again bypass the calculus 3 by saying the line integral of dl simplifies to L. And then the last step was to do some basic algebra, some basic literal equations, and recognition that the path length is equal to the circumference, subbing in the circumference, and then deriving a final equation. So that's one of the simpler derivations, but I hope that helped you guys out, and I hoped that you understood a little bit more of this equation, of this derivation. Even if I couldn't give you guys a lot, I'm still glad that I was able to help you in whatever way I could. So I'll catch you guys in the next one, and you guys have a great day.